Hello everyone, my name is Wesley Assunção and I'm going to present this piece of work towards a microservices-based product line with multi-objectives evolutionary algorithms. In this work we bring together two different concepts: microservices, which is an architectural style to develop an application composed of a set of small, autonomous and independently deployable services that work together, and software product lines, an approach to create a family of software products mainly with focus on reuse and customization. Despite the synergy between these two concepts, we can observe in literature only a few words investigating this synergy. Still, there is not an automatic approach to support the designing of microservices-based product lines. In the way to move towards a microservices-based product line, we want to answer this question: how can similarities and variabilities among different microservices-based systems be automatically identified? So, to answer this question, we proposed MOEA4MBPL, a multi-objective evolutionary algorithm for microservices-based product line. This approach aims at leveraging interoperability and allowing functionality reuse. So it is a first initiative to extract feature models from existing services. And in this way, we can have feature models to be used for defining, designing, and support the implementation of microservices product line. Since this is a complex task, we propose the use of multi-objective optimization. Here we have an overview of the two pieces of information used as input. For example, we have a matrix describing the systems using as input with the features they implement. We can see different configuration of features for each system. And then we have a dependency graph which describes the dependencies between different microservices. Our approach uses multi-objective evolutionary algorithms as, for example, NSGA-II and SPEA2, and it has as output a feature model that is a tree-like representation of the features of a software product line in the way that you can combine them to derive a product. So it represents how the features are organized and how we can combine them in a new product. For the evaluation of our approach, we rely on 6 different open source microservices-based systems, from which we could observe 14 different features or microservices. We have here in this table, in the columns, the systems, in the rows, the microservices. This is a summary of the results. In the table, we can see that you have used 3 different performance indicators: hypervolume, HV, Euclidean distance to ideal solution, ED, and runtime. The results are based mainly on the average and the standard deviation, as you can see in the parentheses. The statistical difference between these two algorithms was computed by Wilcoxon, and we can see that there are different statistical difference in all the cases. The effect size points which is the best algorithms. So here for hypervolume, we can see that in 79% of the runs, SPEA2 obtained the best results. For Euclidean distance to ideal solution, we have a different result, in which NSGA-II obtained the best values. In this analysis, you can observe that for hypervolume, which considers all the solutions in the Pareto front, it seems to explore better the search space. On the other hand, for Euclidean distance to ideal solution, NSAI HV seems to perform a better exploitation of the search space. Regarding the runtime, as expected, NSGA-II obtained the best values. This is because SPEA2 uses mechanisms to control and archive the best solutions. This requires additional resources, so it has a worse runtime. These are two examples among the set of best solutions obtained by the algorithms. As you can see, they have different values of precision recall, and in this case both of them also have the same value of dependency conformance. In other words, they do not break any dependency that you have in the dependency graph. Also, having the same value of recall, from both of them you can derive products that are desired in the input. But on the other hand, they do not have so much good value for precision, so they have a surplus of products that can be derived. This is just two examples. So, considering all the obtained feature models, we can say that they represent the desired microservices-based systems. So the software engineers can select the best ones according to their needs. And since SPEA2 has the best values for a hypervolume, we can see it explores better the search space. On the other hand, NSAI has the best values of Euclidean distance, so it has a better exploitation of the search space. For future work, we want to explore new objective functions using different information, as for example non-functional properties, and of course to create new architectural models in addition to the feature model. Yet we want to perform new analysis using different algorithms and different systems. Thank you for watching, and if you have any question or if you want further information about this paper, please get in touch with us. Bye.